Students, this is again a question about DC shunt DC motor, and it has given different kind of the rated values, and it has given the field current of 5 ampere brush. So the question is about power is output from the motor at its rated condition and efficiency. So whenever we have the question about the motor, how much power is being output from the motor, one of the most important thing that we must be knowing at this time is the motor's power flow diagram. How power flows inside a motor. So actually, as we see that the power flow diagram, the input to a motor, so here if we have the motor, the input to the motor is basically the power we are giving at the terminals. So the input to the motor is actually P in is a V terminal and I terminal. This is also the line current, we can call it. Now inside the motor, for the motor, the first kind of losses that exists are I square R losses, and these I square R losses in the winding. After this, we can see the losses that exist inside the motor. So for the motor, after the losses in the winding, we can assume that the power is now converted, and this power is converted into mechanical power. So first our losses were I square R losses, and then the voltage, the power is converted into mechanical power, and then the electrical power is converted into magnetic power, and magnetic power is converted into mechanical power. So this converted electrical power to mechanical power can be represented as torque induced into mechanical speed. So the voltage and current that were induced in the rotor are now converted into torque induced into speed. So this is known as P converted. This is the power that is converted from electrical to mechanical. Once this power is converted, further losses also exist in the machine. What are these losses? Now these losses, we can call them core losses. That is due to the magnetic effects. We can couple it here. They are called, the next type of losses are called mechanical losses. They are also known as rotational losses. And the last losses are called stray losses. These losses are miscellaneous losses that we assume 1% or 2% to be existing in the machine. After that, we get P out, and P out is actually equals to applied torque. Look, this is applied torque. Here the torque was induced torque. And we have the mechanical speed at the output. So this is how power flows through the machine. So we have the electrical losses, and then we have the mechanical side losses. Now for the shunt DC motor, we know that this is V terminal and this is I terminal. This is IF and this is IA. So if we are able to calculate armature losses, we can calculate how much power is being lost. We can calculate the first kind of losses, that is causing the copper losses inside the machine. So let's calculate. Let's see that our RA, armature, the armature resistance of the machine, it is saying when a rotor is blocked, an armature voltage of 10.2 volts produces 170 ampere of current flow, and a field voltage of 250 volts produces field current of 5 amperes. So it is saying that, for example, if we have our rotor of the machine that is not moving means EA equals to 0. So if our this is equals to 0, so Vt equals to, we know that in shunt motor Ea plus Ia Ra. So if this is equals to 0 for a terminal voltage that it is telling us 10.2 volts. So and the armature current of 170 amperes flows when we lock the rotor. Lock rotor means it is not moving. So the armature resistance will be 10.2 volts divided by 170 amperes, that is 0.06 ohms. Okay, we are calculating this because we have to calculate the armature losses. The second is field resistance. And what about field? It says field voltage of this produces a field current flow of 5 ampere. So voltage is 250 volts and a field current 5 amperes is flowing. So what is RF? RF will be 50 ohms. So we have calculated these two resistances, RF and RA. Now we require at rated conditions. So for the rated conditions, if we are able to calculate both the losses, then it is done. So now it is given in the question that for the rated values, the rated field current is 5 ampere and rated armature current is 170 amperes. So we can calculate the values for armature losses. P armature loss is actually equals to I armature square into that is IA rated square into RA, and it is 170 square into 0.06. So P armature loss equals to 1734 watts. Actually, we are calculating copper losses. We must remember this thing. And why are we calculating copper losses? How much power is output from this motor at rated condition? So what we are trying to find is output power of the motor. And to calculate the output power, we have to subtract all the losses that exist inside the motor. So we are able to form basically P out is equals to P in minus P loss. So we are calculating the power losses. Second type of loss that exists is in the field, and this will be equals to we know the field current IF rated square into RF, and IF is, we have calculated, it is given is 5 square, and RF we have calculated 50. So PF field loss is equals to 1250 watt. So we have the total core losses in the machine will be equals to this. But there is another important aspect, that the brush voltage drop is assumed to be 2 volts. So this is another kind of loss. Sometimes it is mixed with the copper losses, but in here he has separately mentioned the brush voltage drop. Which brushes is he talking about? He is talking about the brushes that voltage drop exists at this side, where on the rotor we have commutator and we have carbon brushes that is actually making a contact with the commutator. So it is saying that there is a brush voltage drop also. So when the motor goes, there are 2 volts voltage drop exists on the brushes. So we can calculate the brush drop as voltage drop into the rated current that is flowing through the brushes, and that is going to the armature, and this is actually 2 volts. So this power that is lost over the brushes is actually 340 watts. So we have calculated the I square R losses. Now the question arises how to calculate these losses, the core losses or the mechanical losses that are existing inside the machine. So first of all, for this condition, he has here expressed a very interesting case. He says that at no load, when there is no load connected to the motor, so we have a motor and it is not rotating any object that is connected to it. At no load, this motor armature current, when I connect this motor without any connected load and I apply a voltage of 240 volts, despite there is no load connected to the motor, this motor is drawing a current of 13.2 amperes. So why is it drawing that much current when the motor has no load connected to it? So actually this current that is being absorbed by the motor is actually to overcome its rotational mechanical losses and also the core losses that exist in its core due to eddy current and hysteresis losses. So when the machine is not moving any load, but it is taking up the current, this is actually the current that the machine is using to overcome its mechanical losses and the core losses. So I can say that I call this if mechanical losses plus P core losses is actually equal to the power that is being drawn by the motor at no load. So this will actually become equals to 240 volts and 13.2 amperes. So this losses will be 3168 watts that the machine is drawing. So this is another type of the loss that the machine is now. So we are able to calculate core losses and mechanical losses. Now stray losses for the machine are usually P stray are considered to be 1% of the rated power. So what is the rated power of the machine? Rated power, we can see the rated armature and the rated field current of this. So the rated power of the machine is actually the total voltage that we apply to the machine, that is 250 volts. Total rated armature current, that is 170 volt plus 170 amperes plus the field current 5 ampere. These both are being supplied by the battery. This is actually equals to the I terminal 175 ampere. So the rated power that the machine is taking is actually the input power of the machine. So for example, this was at no load, and if I draw the motor at full load, for example, here is the motor and it is driving a heavy load and it is connected to the terminals of a battery. So here Vt is equals to 250 volts and the current that the machine is taking is 175 ampere, 170 to the armature, 5 amperes to the field. So the input power P input to the machine is actually Vt It, and this power is actually this power 250 into 175. This is the rated power and this will be equals to 43,750 watts. This is P into for our machine, and 1% P stray is, so the P stray will be 1% of the rated power, and we can calculate this by multiplying 0.01 with our 43,750 watts, 437.5 watts. Now in this manner I have calculated all the losses, I square R loss, I've calculated core mechanical losses, and I have calculated the stray losses, and meanwhile I have also calculated the input power of the machine. So what will be the output power? P output equals to P in minus all the losses that we have calculated. So we have calculated, we have brush drop losses, we have all the copper losses, we had the mechanical losses and the P mechanical and the core loss, and we have the stray loss. Now let's look at this. What is P in? P in we have calculated, this is 43750 watts. Now what was brush drop loss? Where did we calculate? Here was the brush drop loss, this was 340 watts. What were the copper losses? Copper losses existed in armature loss and the field loss. So this is minus, this is 1734 watt, and we had 1250. We can add them, so we can write what were mechanical and core losses. Both of these two losses we calculated from the no load test, they were 3168 watts. What were the stray losses? 437.5. So if we apply all these, so the P output will be 36,820 watts. This is the output power of the motor. And if we want to calculate the efficiency now, the efficiency of the motor can be calculated simply for the efficiency equals to P out over P in, and this way into 100%. P out we have here, P in we have here, and this ratio will actually become equals to 84.2%. This will be the efficiency of the machine. Hope it helps. Thank you.